in the chat, and I'll make sure that that question gets addressed. So we'd like to welcome Sabrina Huth today. She's a graduate student at TU Darmstadt working on equations of state of nuclear matter for astrophysical applications. So take it away, Sabrina.
Thank you. Thank you very much for a nice introduction. So I'm very excited to present to you now the latest result or project that I've been working on for the recent years, and that's about the equation of state for astrophysical applications. So the equation of state is a key microphysics input in both core-collapse supernovae, but also neutron star merger simulations. And in these simulations, you really have a broad range of density, temperature, but also electron fractions that are reached. And especially over this broad range of densities, the equation of state is still rather unknown. So this especially applies for densities above nuclear saturation density. But nevertheless, the overall goal is, of course, to have equations of state for these astrophysical simulations that are consistent not only with nuclear physics, but also with observations. And for this, in the first part of my talk, I will show you a study of the impact of nuclear physics input in core-collapse supernova simulations. And then in the second part, I will go deeper into a new equation of state functional. So we improved equation of state in order to be consistent with the constraints we have from nuclear physics as well as observations, and then also to generate AOS for astrophysical applications. So in fact, there have been already studies about the sensitivity of the equation of state in core-collapse supernova simulations, and I show you here results from 1D simulations that we did with the flash code and the M1 neutrino transport scheme using a 15 solar mass progenitor star. So on the left, you see the proto-neutron star radius, and on the right here is the shock radius. And for this, we use two different AOS that are commonly used in supernova simulations, which are the Latimer-Svesti AOS, here denoted as LS220, the 220 just stands for the incompressibility. And the other one is the Shen AOS. And for the proto-neutron star contraction, you can see that when you use the softer LS AOS, then at the end, after roughly half a second in the simulation, you end up with, let's say, 5 kilometer less of proto-neutron star radius compared to the stiffer Shen AOS. And due to this faster contraction with the Latimer-Svesti AOS, we then get an explosion in our simulation, so the shock radius increases with time. And for the Shen AOS, we don't see an explosion, so this will collapse to a black hole. And in this first study, we showed that the proto-neutron star contraction is mainly governed by the nucleon effective mass. This means if you use the underlying theory of the Latimer-Svesti equation of state and then only vary the nucleon effective mass, for this we have here two models. So the M star 0.8 refers to a model based on the LS AOS, but uses a value of 0.8 at saturation density for the effective mass. Then with this lower value of the effective mass, your proto-neutron star radius increases. And if you then use this M star S model, which uses the same effective mass as the original Shen AOS, then you indeed get a proto-neutron star radius that agrees with the one from the Shen AOS. However, at the same point, we still see explosions for all of these models. So there is still some difference compared to the original Shen AOS. And now in the first part, I will explain you more in detail what's actually going on here and why we get this result. So for equation of state used in core-collapse supernova simulations, you have two different underlying models generally that are used. Here, the Latimer-Swesti AOS is based on a Skyrme energy density functional, and the Shen AOS uses a relativistic mean field model. But on top of this, also all AOS that are available for simulations, you have a wide variety of nuclear matter properties that are applied. And what are these nuclear matter properties? From nuclear theory up to around roughly saturation density, you can expand the energy per particle around saturation density, and this is a symmetry parameter beta, which is basically just the difference of neutron density to proton density. And then you end up in this Taylor expansion here, which you see also in this figure here. So the energy per particle as a function of density. And for symmetric nuclear matter, when you have the same amount of neutrons as protons, you have this red curve here, which has a minimum. And this minimum defines your saturation density and the binding energy. And the curvature around this minimum is given by the incompressibility K. Then for pure neutron matter, you have only neutrons and no protons. And this can be characterized by just two parameters, or the most important parameters are here. The symmetry energy, which is the difference in energy from pure neutron matter to symmetric nuclear matter. And then you have this L parameter, which gives you your slope of the energy at saturation density. And nuclear theory estimates these parameters with uncertainty ranges, which you can see here in this table. So the bottom, the green numbers here for symmetry energy, slope parameter, incompressibility, and effective mass are estimated by nuclear theory. And this part here on top for the saturation density and binding energy, this is the empirical saturation point. And then you also see here the values for the LS220 AOS and for the Shen AOS. And so the details don't really matter here, but what's important is that you see, especially here, for example, for the slope parameter, that the Shen AOS and also to a lesser extent the Latimer-Swesti AOS are way above the predictions from nuclear theory, which is here in turn calculated by chiral EFT. So this is an ab initio calculations. And especially here, the effective mass there, chiral EFT predicts a value at saturation density of roughly 0.8 or 0.9, but the Latimer-Swesti AOS does not explicitly use an effective mass. So here the effective mass is set to the bare nuclear mass, and the Shen AOS uses a value that is rather low, so a value of 0.634 at saturation density. And now what we did in this study is that we took the Skyrme energy density functional from the Latimer-Swesti AOS, and this you can see here. So this functional depends on density, proton fraction, and temperature. The whole temperature dependence is basically given by this kinetic energy density tau here. And this whole first part of the functional gives you your kinetic energy. And here also the effective mass enters, which is for this AOS expressed in terms of a density dependence. So you have here an alpha parameter with which you can use to tune your effective mass. But as I said before, in the LS AOS, this alpha parameter is set to 0, such that the effective mass is just equal to the bare nucleon mass. Then all the other terms here correspond to your effective interaction. So these A, B, C, and delta are called Skyrme parameters, and we use them to fit them to specific nuclear matter properties. So we individually set the effective mass, incompressibility, symmetry energy, binding energy, and saturation density to values basically whatever we like. And then we calculate the Skyrme parameters. And with this, if we have the Skyrme parameters, then we can compute equations of state tables. And for this, we use the code from Schneider and co-workers. And with this framework, we can now systematically vary one nuclear matter property by one, and then see how this affects the outcome of the simulation. In turn, we use several models where we vary all nuclear matter properties from the value of the Latimer-Svesti EOS to the values adopted in the original Shen EOS. So this first model here is just the original Latimer-Svesti 220 EOS. Then this M*** 0.8 model that you've seen before uses a value of the effective mass at saturation density of 0.8, but all other parameters here are still the same as in the original LS EOS. Then for M***S, we use the value of the effective mass of the Shen EOS. And then in the next three models, we vary on top of the effective mass also here the incompressibility or the symmetry energy or both to the value of the Shen EOS. Then we have one additional model which is called SK Shen because it uses all values for nuclear matter properties from the Shen EOS, but it's still the underlying model from the LS EOS, so it's still based on the Skyrme energy density functional. And now again, let me show you the results for the proto-neutron star contraction. So now first for the different effective mass models that you have already seen before. So here again, if you lower the value of the effective mass, then your proto-neutron star increases, and so the radius of the proto-neutron star increases, which means that the proto-neutron star contraction slows down. And this then leads to a smaller shock radius. And the reason for this is that if you have a faster contraction, then the temperature at the surface of the proto-neutron star will increase. And by this increase, the neutrinos that are emitted at the surface are more energetic, such that they can, such that if they are absorbed right behind the shock, then they basically can put more energy to the shock, and therefore the radius of the shock or the shock wave can further evolve to higher radii, and therefore this leads to an explosion. Okay, so this again shows that the effective mass is really the key quantity that governs the proto-neutron star contraction. Nevertheless, what's really important here is if we won't use any heating factor in the simulation, so that so the shock radius for every simulation would basically look the same because they would all collapse back to a black hole, then this here for the proto-neutron star radius, this would still look the same. So we would still see this pattern due to the effective mass. If we then use all other models where we also vary the incompressibility, symmetry energy, and the saturation point, and you see for the proto-neutron star radius that this has only a minor impact. So this means that all models that use the same effective mass basically end up in the band here for the proto-neutron star radius. But we see some difference here for the shock radius. And here it's especially important to note that if we further vary the saturation point, so if we use the model SK Shen, then we also have no explosion here in the simulation, which is similar to the original Shen EOS. In order to understand this behavior, we have a look at the central pressure. So here you see central pressure as a function of central density. And in general, the pressure is inversely related to the effective mass. So this means if we lower the effective mass here from the LS AOS to m star 0.8 or m star s, so m star Shen, then the pressure will be increased. And similarly, if you use a larger incompressibility of the Shen AOS or also the larger symmetry energy, then you further increase your pressure. And when you now compare the pressure from the SK Shen AOS and the original Shen AOS, then you see that they are quite similar here. And this means that in this study, the nuclear matter properties are more important than the underlying model. So in this case, it's more important which nuclear matter properties you take instead of if you use a Skyrme energy density functional or a relativistic mean field. But this distinct behavior of the proto-neutron star contraction due to the effective mass, the reason for this is given by the thermal effects. So we can calculate the thermal index by separating the pressure and energy density into a cold and thermal part, which you can see here. And then the thermal index is just 1 plus the ratio of thermal pressure to thermal energy density. And this means that you have here the total pressure minus your cold pressure. And in the simulation, we can actually use this expression to calculate the thermal index, because the pressure and energy density we just get out of the simulation at any density, proton fraction, or temperature that's just reached within the simulation in the trajectory. And then we get the cold pressure and the cold energy density just from using the same density and electron fraction, but the smallest temperature that is available in the equation of state table that we use for the simulation. And the results for the thermal index are shown here as a function of density. And below roughly half saturation density, you get a thermal index that actually depends on also symmetry energy and incompressibility, because you have clustering there and alpha particles and nuclei and so on. But if you have homogeneous matter, which is there above roughly half saturation density, then you have here for the baryonic contributions only neutrons and protons. And here you see again these bands due to the effective mass. So this blue line is just the Latimer-Swesti EOS. Then this green line here is our model m star 0.8. And then on top of here, you have all AOS that use the effective mass of the Shen AOS. So here you also have the models with different symmetry energy and incompressibility and so on, but they all end up with the same thermal index. And this actually agrees perfectly with an analytic limit for the ideal Fermi gas for density dependent effective mass, which is just this simple expression here for the thermal index, which only depends on the effective mass and its density derivative. And we also plotted this here in these gray bands, and you really see this perfect agreement. So this again points out that the effective mass determines the density dependence of the EOS. And with this, the effective mass governs the thermal contributions to the pressure, and therefore the proto-neutron star contraction behavior. Okay. But what I've shown you before also was that we used the Latimer-Swesti and the Shen AOS, or we changed all values for the nuclear matter properties from the Latimer-Swesti to the Shen AOS. But in this table here, you saw that the nuclear matter properties are not really consistent with nuclear physics. So especially here for the slope parameter, but also for maybe saturation density of the Shen AOS or the very large symmetry energy of the Shen AOS. And of course, here the effective mass is also not consistent with ab initio nuclear theory. So in the next part, we now use the knowledge from the first study to generate new equations of state, a new equation of state functional, and then also equations of state that can be actually used in astrophysical applications and that are consistent with nuclear physics as well as observations. And for this, we came up with a new energy density functional, which you can see here. So in the first part, this is exactly the same basically. So you just have your kinetic term, but then we now have a different functional form for the interactions. In particular, you see here that we don't have just this density dependent in the numerator, but we also have this here in the denominator. And we choose this functional form because this ensures a very good fit performance. So our fit is very stable, even if we vary the input parameters by a lot. And now, of course, we also have some new parameters here. So this D parameter and, for example, and this delta I, so the density exponents, we choose, and we choose them in a way to actually generate this stable fit performance. And we in fact use two different density exponents. So first, we use this delta IKF, which is basically, if you plug this in, like an KFA expansion. And then we have another set of delta I, which is called delta IN, because if you plug this in, then you just have powers of densities. And for each of these choices, so for either delta IKF or delta IN, we then have 4 different possibilities for the D parameter. So you choose either for delta IKF, for example, 1, 3, 5, or 7. But it's important to note that the specific values of these D parameters won't really change at the end the outcome of our AOS functional. But the details of this I can also explain later. Then the actual fit parameters are these AIs and BIs. And since I goes from 1 to 4, we have 8 fit parameters in total, which we can now fit to basically whatever we like. So we choose 5 nuclear matter properties: saturation density, binding energy, incompressibility, symmetry energy, and slow parameter. And then we fit 1 more parameter at low densities. Here we use the energy of pure neutron matter. And this is at very low densities from accurate quantum Monte Carlo calculations. And then we have 2 more parameters, which we fit to the pressure of pure neutron matter and symmetric nuclear matter at high densities. And our goal is, with this study, that we fit all these parameters and then we vary them according to the uncertainties we have, for example, for the nuclear matter properties. And if we do this, then we can basically span, we get an equation of state functional that can span the whole uncertainty we have from nuclear physics as well as observations. So in order to do this, we of course have to first discuss the constraints that we actually use for these nuclear matter properties and also for the pressure at high densities. So in the functional, you saw that the first term includes the nucleon effective mass. And as I pointed out in the first part of my talk, an accurate implementation of the effective mass is really crucial to capture the important thermal effects for the proto-neutron star contraction. And just recently, there have been new results from ab initio calculations at finite temperature using chiral effective field theory from Ariana Carbone and Achim Schwenk. And you can see this here, and it's plot for the effective mass as a function of density. This blue line here is their result for pure neutron matter, and the red line here is the result for symmetric nuclear matter. And chiral EFT is only valid up to roughly 1 or twice saturation density. This is why the results stop here. And in previous equations of state that are available for astrophysical applications, you could only use the mean field equation effect of mass that basically only decreases with density. So you had this one parameter which fixes the value of the effect of mass at one density, say saturation density, but then it will just further increase if you, it will further decrease if you increase the density. And now what's new for these results is that you have this turnover behavior for both pure neutron matter as well as symmetric nuclear matter at roughly saturation density. This means that your effective mass increases again and does not only decrease with density. And this is actually due to 3 nucleon forces from the strong interaction. So, but this also means that we need a new effective mass parametrization that now not only depends on density, but also on proton fraction. And this new parametrization you can see here as these gray lines. But since we only have the results until trisaturation density, we don't know anything about of the high density behavior. And therefore we just investigate here 3 different scenarios that just cover a broad range at high densities. Okay, then let's come again to nuclear matter properties, and here more specific to constraints we use from nuclear physics and also the uncertainty you have from this. So for symmetric nuclear matter, we have these 3 parameters: saturation density, binding energy, and incompressibility. And so these 2 here is just the empirical saturation point. And this value here comes from chiral EFT, also with an uncertainty. And we just use the values and the associated uncertainties to generate 3 triples of these 3 parameters that then cover the whole range of the uncertainty. Then for pure neutron matter, we have the 2 nuclear matter properties, symmetry, energy, and slope parameter. And here you can see results for the energy per particle as a function of density for various calculations from chiral EFT. So all of them are based on chiral EFT, but they use different many-body methods or also different orders in the chiral expansion. But nevertheless, you see that they agree, so they all overlap, and they are actually associated with uncertainty band. So our goal is here with fixing the symmetry energy and the slope parameter that we can in fact cover the whole uncertainty band from these calculations. We also show here the energy of the unitary gas as this dotted line, because Ingo Teves and co-workers pointed out also in a paper from the last years that the unitary gas can be used as a lower bound for pure neutron matter. And in fact, you see here that it actually shrinkens a bit the uncertainty, at least for 2 calculations from chiral EFT. The others are not affected by this. Some of these calculations also give ranges for the slope parameter and the symmetry energy at saturation density, so for the symmetry energy slope correlation. And basically the original plot has been first made by Latimer and Lim in 2013, and then also in a recent paper kind of extended from Christian Drüschler and co-workers. And we now show here basically the same plot, but with, let's say, less information. So in order to don't overload everything, we basically show here the microscopic calculations, and we have, as an example, also an additional constraint on the symmetry energy slope correlation from experiment, and here from nuclear mass measurements. Okay. So this, here we have 4 different calculations, which you can see here, and this H from Hebeler and co-workers, and TK and also GPB. These are actually 3 calculations that I showed you already in the last plot for the energy per particle of pure neutral matter. And then we have here an additional one from Gandolfi et al. So all of them are again based on chiral EFT, but they use these different many-body methods, and then they also come up with different ranges and also uncertainties for the slope parameter and the symmetry energy. But what I want to point out here is that all of them are consistent with the unitary gas boundary here from Teves et al. Okay. And now, based on this, we chose 4 pairs of the symmetry energy and the slope parameter that you see here as these green dots, in order to span a quite broad range of this theoretical uncertainty. But in order to really come up with these 4 specific points, we actually did another study. So for every combination of slope parameter and symmetry energy, we calculated all different equations of state. And what I mean with this is that we just varied all other nuclear matter properties, the effective mass, the different delta I's that we use, and the different D parameters, and also different high density fit points. We varied all of them, and then at the end we looked up how many of these AOS that we calculated are actually consistent with the constraints that we have from nuclear physics and from observations. And this is what you see here in the color coding. So the actually numbers here don't really matter, but you see that here in the middle, you have a lot of AOS that are consistent with the current constraints from nuclear physics and observations. And now if you put these 2 figures together, then you can see that the 4 pairs we have for symmetry energy and slope parameter do in fact cover a broad range of the uncertainty from nuclear theory, but we also can generate with this a lot of AOS that are consistent with the constraints. And to show you actually that they cover the whole pure neutral matter uncertainty band, I show you here 4 panels for the energy per particle as a function of density. Every panel corresponds to 1 pair of symmetry energy and slope parameters, but I won't go into details here. It's just for you, when we here use the smallest symmetry energy and slope parameter, then you see that in fact we are at the lower end of the pure neutral matter uncertainty, so right on top basically of the unitary gas energy per particle. And if we use a large symmetry energy and slope parameter, then we can cover the upper pure neutral matter uncertainty boundary. So with these 4 points, and also the uncertainties from saturation density, binding energy, and incompressibility, we cover the whole uncertainty from nuclear theory. And also to note here is that, again, the unitary gas is here set as a lower bound for pure neutral matter. So you also have here a couple of gray depicted AOS, and they are actually excluded because they are below, they have energies below the energy of the unitary gas. Okay, then as I mentioned before, we have two other parameters that we fit to the pressure at A times saturation density for pure neutron matter and symmetric nuclear matter. And in order to set these fit points, or the ranges to which we want to fit actually the pressure, we have here another study by Leonard et al., who calculated for the first time the equation of state of symmetric nuclear matter at intermediate densities from first principles. So this is done using functional renormalization group, and this method is completely based on QCD. And here you see the results from them. This is the pressure normalized to the pressure of the free quark gas as a function of density. And here at low density, you have again results from chiral effective field theory. And then here, starting at 3 times saturation density up to roughly 10 times saturation density, you see as this red band their result from functional renormalization groups, so from FRG. And they also give an uncertainty band with the result, and this is obtained by varying the G scale in their calculations. And what's really remarkable here is that you really see a great consistency with the chiral EFT results. So actually you could basically just extrapolate, and then you will have here an AOS that can overcome this gap. And also towards high density, it's consistent with results from perturbative QCD, which you see here in green. In their paper, they also showed what they get for the speed of sound. And for this band, if you calculate the speed of sound, then you actually see a maximum in the speed of sound above 1/3. And this is very important for heavy neutron stars. So if you wouldn't have this maximum, then you couldn't generate neutron stars above 2 with masses above 2 solar masses. Okay, now let's come to constraints from observations. Because of course, now I've already just talked about nuclear physics, but at the end, if we generate an equation of state, then we also want that this covers the whole uncertainty from observations. And from this, we use the joint analysis from Reimarkas et al., who give in their study a 2 sigma band, where they use the information from the 2 solar mass measurement, or 2.14 solar mass measurement from T et al., the GW17 or 817 results, and the new NICEA results. And here you see the mass radius relation, and here the EOS, so the pressure as a function of energy density, for 2 different equation of state models. So up to saturation density, it's also based on chiral EFT, and then in order to extend the EOS, they use either the piecewise polydrops model or a speed of sound model. And I won't go into details here. What's just important is that they give 1 sigma and 2 sigma bands if they include all the information from the heavy neutron star, gravitational waves, and NICEA. And we will use the 2 sigma bands in our study to discard the EOS. So when we generate the EOS, we will just look up if our EOS is consistent with the 2 sigma band from the study. So if the pressure is just within this 2 sigma band, and if yes, then everything is fine. And if the pressure is, for example, higher, then we will just disregard it. And of course, additionally, we also use a constraint for the functional that every EOS needs to support a 2 solar mass neutron star. And for this, we use the measurement from Antoniades and the 2 sigma uncertainty from T et al. And then let's look at our results for the AOS functional. So in order to get these bands, we now put every variation together. So we have the 3 different effective mass scenarios for high densities, the variation of nuclear matter properties, the variation at high densities in order to cover the band from observation, and also from the functional, the different density exponents, as well as the different D parameters. And if we combine all of these variations, then we generate thousands of EOS, and then we only keep those that are consistent with all constraints. And this is what we get here for the pressure as a function of density. And in light gray, you see the band from Reimarkas et al. So from the study, from the observations that I've shown you before for beta equilibrium, so for neutron star matter. And you can really see that our AOS functional can basically cover the whole band from Reimarkas et al. There's just a difference here for softer AOS, and this is basically because we use this fixed constraint for a 2 solar mass neutron star, and they use actually a likelihood function. So this is why we get here a little bit different results for softer AOS. And then you also see here the speed of sound as a function of density. And the color coding for both is that until masses of 1.4 solar masses, we have this dark green band. And here you see that this is pretty narrow for the speed of sound. And then if we go to higher densities, so up to the maximum mass of neutron star, you have this light green, and there the speed of sound already covers a quite broad range. And then at even higher densities, so where the neutron star is not stable anymore, and we actually can cover for the speed of sound a range from, let's say, 0.2 until almost the speed of light. And for here are then the results for the mass radius relation. Here on the right, mass as a function of radius. Here you see the pressure again, but now as a function of energy density. So this is the equation of state. And yeah, of course, the mass radius relation is now calculated by solving the TOV equations. And here on the left, you see again that we cover a quite broad range of the uncertainty band from Reimarkas et al., which is also, of course, reflected here for the mass radius relation. But it's also interesting that we actually get a little bit larger maximum masses here. So there are some AOS that are stiffer, even though they lie within the band from Reimarkas et al. And then we use now also the FRG constraint. So in orange, you see all AOS that are actually consistent with the functional renormalization group calculations for symmetric nuclear matter. And you see that if one incorporates this FRG results as a constraint, then this actually narrows down your uncertainty in the mass radius relation and in the AOS. So this FRG results can really be used as an additional constraint for the equation of state. Then from the mass radius relation, we also show here a histogram for the maximum mass. So here's the number of AOS with a specific maximum mass, and we have a broad peak here. It's a little bit a bimodal function with two peaks, you could say, and then it falls off steeply after roughly 2.4 solar masses. And this is actually consistent with a maximum mass boundaries, so for the upper bound of the maximum mass that are inferred from the gravitational wave measurement, which give an upper bound of roughly 2.3 to 2.4 solar masses. Okay, with this, let me quickly summarize. So in the first part of my talk, I've shown you that the effective mass is the key quantity that governs the proto-neutron star contraction. And from this, we argue that an accurate implementation of the effective mass is very crucial in order to capture the thermal effects. And this is why we came up with a new effective mass parametrization that is based on ab initio calculations. And this is then implemented in our new equation of state functional. And with this functional, we can actually interpolate between low density and high density, but under very stable and flexible conditions. And therefore, we can cover the whole band or the whole uncertainties from nuclear physics and observations. And if we now, as a next step, use this AOS functional and implement it in a finite temperature code in order to generate representative equation of state tables that can then be used in Corpolab supernova and neutron star merger simulations, then you can actually see what is the whole sensitivity of the AOS in these astrophysical simulations, because then you can transfer the uncertainties that you have from nuclear physics and observations on the AOS. You can transfer this in your simulation. And at the end, I also showed you that if you use the functional renormalization group results and constrain with this your AOS, then this can further narrow down the uncertainty also for the mass radius relation. And with this, let me thank first my collaborators, especially Corbinian and Hannah, and then thank you for your attention.
Thank you so much for sharing your work. This is very impressive. Yes. We now have time for questions, so feel free to jump in and we'll get those answered.
Hi, Sabrina. This is Sanjay here. I must first apologize for missing the first half of your talk, but I enjoyed
this. You already know from Hirschek.
Yes, but still, it's impressive, and it's nice to see an exploration of key effects that influence proto-neutron star evolution, and especially the thermal effects. My question is more related to FRG, and while your low density equation of state is informed by chiral EFT, and chiral EFT is in turn informed by a lot of scattering data and a lot of data on nuclear structure. I am wondering, what is it that what are the experimental or what are the firm theoretical constraints that would make me believe that FRG is actually giving us, really stringent guidance as opposed to being a model?
So in this study that I introduced here, this is really the first calculation. So what they do is they start from the QCD action, and then they evolve down with the RG flow. But they use actually 4 quark couplings, but so far they only use 2 massless quark flavors. So of course, since it's also the first study, there are still some uncertainty and everything in there from things that they have not incorporated yet. But it's so why we use this is because it's the first study from calculations based on QCD in this intermediate density regime. So far, there has been nothing like this for densities above twice saturation density.
No, I understand. Maybe you mentioned this earlier on, but there is a distinction between a calculation that has some internal consistency and experimental validation, and another approach where it's a first approach, but a lot of open questions.
So regarding the with experiments and what you said in your question, so I'm not an expert on these calculations, so I can't really tell you if they use any. So as far as I know, since it's from first principles, I think there are no experimental values that go in their calculations. But I'm also not completely sure here.
Okay. Thank you.
No problem.
Any other questions?
Okay, if there are no other people asking questions, I'm happy to keep jumping in here.
Fire away.
So this is the equation of state, and is anybody at Darmstadt or maybe you trying to use this equation of state framework to also consistently calculate the neutrino interaction rates for astrophysical simulations?
So far we haven't done this, but since I'm in the middle of my PhD, maybe this might be a next project. Of course, it's desirable to have both microphysics inputs, so the equation of state and neutrino matter interactions, to have this consistent in your simulations. So I think this would be very nice if you, for example, also use the effect of Mars that we have here and also implement this with the neutrino interactions.
Okay. Yep. Yeah, maybe you should plan on visiting Seattle sometime when this COVID nonsense is over, and we could discuss how to do some of these neutrino interaction rates.
Yeah, this would be great, actually. But let's see when this is happening. So probably after a vaccine or something like this. But it would be very great to work on this, to have all the microphysics consistently. Yeah, that's definitely a big goal.
Any other questions? There aren't any in the chat, so feel free to type them out if you don't want to ask yourself either. So I had a question on your slide 14, if you don't mind jumping back a little bit. So I may have misunderstood, but it looks like on this plot on the right, the 4 points that you've picked out here don't hit on these most common number of EOS bins, if that makes sense. Were you trying to choose more extreme values or sort of sample the space evenly?
Right, so we wanted to use 4 points. We didn't want to use 10 or 12 or whatever. This would just be too much, but we basically looked at both plots. So here you have the uncertainties from theory, and here you see how many EOS are consistent with the constraints. And then we looked for combinations that both generate lots of EOS that are consistent with constraints, but also capture all the uncertainty range here from the theoretical calculations. So, for example, this 1 point here is just one, let's say, extreme point where you have really small symmetry energy and slow parameter. And then we also have ones that are larger. Actually, here from this plot, you see that if you go even larger, then at some point you don't have a lot of EOS that are consistent, because you actually are, you generate energies that are larger than your pure neutron matter uncertainty band. So, but yeah, it's both together, being in this uncertainty band here from all calculations and still having lots of EOS. But of course, if you would say like, hey, I would like to have an AOS with symmetry energy 32 and a slope parameter of 45 or 50, then we can just plug this in and generate this AOS, and then it's fine. For this study, the important point is just to capture the whole uncertainty band.
Okay, so do you plan on providing a code or something to produce these equations of state, to produce the tables for simulations? Or are you going to provide just a couple of tables yourselves?
Yeah, so the first step is to generate AOS tables. For this, we of course have to implement the functional into the code because it's a completely new function, and also the effective mass parameterization has to be implemented there. And when we have this, we will definitely compute some representative AOS. So these are AOS that cover the uncertainty range for the mass radius relation, but also the uncertainty range in the EOS uncertainty itself, and so on. And those we will provide definitely. So, but we haven't really talked about this. So maybe we also provide the code. I don't know, we just haven't talked about this. So. But there will be AOS published, definitely.
Great, as long as something's available, right?
Yeah, so this study is, I mean, you see it's still in preparation, but so we want to submit it to the archive next week, actually, so that the theory side is basically available. And then as the next step, we do the final temperature AOS for the astro applications.